Okay, let's look at example 4 here. They go with this whole thing. This O is the center, which makes these two radii. They tell us that all these lines, PS, PTR, PQ, PR, and QR, are tangents to the circle. Prove the PSOT, prove that it's a cyclic quad. Well, we've got a lot of 90 degrees things going on here because this is a tangent and that's a radius, so T1 and T2 must be 90 degrees. That's what they start off with. And S1 and S2 must be 90 degrees. And what are those three ways? One of the ways is 90 plus 90 is 180. If the angles are supplementary, PSOT is a cyclic quad. And I would like to say the converse of angles in a cyclic quad. If you said that, you could say the opposite angles are supplementary. That's why it is a cyclic quad. But I'd like to write the converse of angles in a cyclic quad. That's why PSOT is a cyclic quad. Now, why is OS tangent to the circle SPE? I don't see a circle, but let's go. SPE. There's no circle, but you have to prove that you could put a circle around here. And that would be true. That would be true if we could figure out that S1 was equal to P2. But we know this is a cyclic quad now, so there's all sorts of things that we can do. Like one of the things, see this S1 here has to equal T1. Well, that's opposite angles those are radiuses, and it's called angles opposite equal radii, right? That's what makes those two equal. Now P2 has to equal T1 because look, they open up to the same segment, angles in the same segment. Well, if that's true, then S1, if S1 equals T1 and P2 equals T1, then S1 must equal P2 because they both equal T1. Well, then we can say OS, if S1 equals P2, we can say that OS is tangent to the circle going through S and P and E because of the converse of the tan-chord theorem. Because the angle between the line and the chord is equal. Because S1 equals P2, that's why you can put a circle around it. But I'd like to write converse of the tan-chord theorem. And there you go.